Question was about Fisher's exact test. Yeah, let me, should I say it in words, or do you want me to look for, words are fine? Okay. So essentially, Fisher's exact test reduces to the null distribution of Fisher's exact test reduces to the hypergeometric. So it says we've got a box of zeros and ones where 1 is the correct thing or the good thing or success or something like that. And we are making draws without replacement from that box and counting up how many ones we have. And so we can exactly compute the p-value, which is the probability. The p-value and the probabilities are given to us through the box, knowing exactly how many ones and exactly how many zeros are in the box. So the only difference between the other exact test with a 0-1 box that we were using and Fisher's is that with Fisher's we are not replacing. So it's draws without replacement. Typically, Fisher's exact test comes from examples where you are looking at a population and you're observing a particular characteristic. You're observing two characteristics. Let's say male and female is one characteristic, and then the other might be on the Dean's list or not. And you see a large number of women on the Dean's list. And you would say, that's just by chance. And you would put, so let's say we have 100 students, and 60 are female, and 40 are male. And you put 100 tickets in the box. And the number of ones you put in there are the number who got on the Dean's list. And let's say that's 30. And so then you draw from that box the number of women, one for each woman. And that would be 60 draws from the box. And you see how many ones you have. And so if you've got more ones than you would expect, then a lot more, then you would wind up rejecting that null hypothesis. So if the 30 people are on the Dean's list and 60% of the students are women, you would expect how many ones to be drawn from the box. You're making 60 draws from the box. There are 30 ones and 70 zeros. So maybe I should actually write it on the board. So the problem we just came up with was that we have 60 women and 40 men. And altogether, there were 30 of the 100 made the Dean's list. And so then the question is, well, we need to know how many women made the Dean's list, right? Suppose 25 women made the Dean's list. And then my question to you was, how many would you expect to have made the Dean's list if there was nothing going on? Yes? 30% of the 60 women, which is, we'd expect 18 to have made the Dean's list. And we got 25. And so now we want to figure out, well, what's the chance under the assumption that there's nothing going on and that the dean's list is like a random draws from a box, what's the chance that we would have gotten 25 women on the dean's list? And whoa. So we make a box, and there are 100 tickets in the box. And now here a 1 is this success, which is the dean's list, and we have 30 of them. And a 0 is a failure, which is 70 of them. And we make 60 draws from the box. And then we do an exact computation of what's the chance draws without replacement. And we make a computation of what's the chance of seeing 25 or more ones in our draws. And we can compute that exactly by our hypergeometric. And our hypergeometric distribution says we need to say how many ones there are. There are 30. How many zeros there are. There are 70. How many draws are we taking? Without replacement, that's 60. And so that's the probability distribution that's going to determine our p-values for us. Okay? Are you going to make a comment? Okay. All right. Any other questions? Yes? Is today's material going to be on the exam? No, but it will help you study for the exam. So the exam will cover up through Friday, and essentially what we got through on Friday were 0-1 boxes for hypothesis tests. And today we're going to get on to hypothesis tests for averages, and we're going to wrap up also with some of our probability. So none of that will be actually on the test, but hopefully it will help you put the material in a broader context. So in a way, it's also concept renewal.
So
yes?
these boxes can be done either with a binomial test or hypergeometric?
So Mike says these boxes can be done with either a binomial or hypergeometric. And Mike, why would you choose one or the other?
Hypergeometric usually have a smaller variability.
Well, I see what you're saying. Well, in this particular case, you couldn't do it with a binomial because we are drawing without replacement, and there's no way. Well, I see what you're saying. Yes. So, in this particular case, I would do it without replacement. But you're right. There are some. If we look at some of these cases. Okay, I concede you could actually probably do this with a binomial as well. And in this case, what you would do, if you did it with drawing with replacement, what you would then say, you'd make a different argument. And so that's the thing about hypothesis testing, is you can, coming up with the null model, there's typically more than one legitimate null models. And what Mike's pointing out is that another legitimate null model would be to say, making the dean's list is it happens by chance, let's say, and that would be a 30% chance. Well, we don't know exactly what that chance is. What we have seen in the 100 people we've looked at is that that's roughly 30%. So I'm going to make an assumption now that 30% of the population gets to go on the dean's list, and now I'm drawing 60 tickets from the box to see how many women made the dean's list, and if 25 is large or not. So that's drawing with replacement, but it's also making the assumption that in the bigger population of all the students at the college or university, that the chance of getting on the dean's list is 30%, and that's an estimated percentage based on our sample. And yes, you could also do that. That's right. Thanks.
I just have a question
Uh-huh. The midterm, what kinds of questions will be, so I'm going to make up a set of sample questions, which I will post, and I'll also post solutions to. But roughly, they're going to be similar to the kinds of questions you saw in your quiz. But there will obviously be questions that, and some of the ones you saw in your homework, except that there won't be any use of R. So the ones where you had to do hand calculations to compute probabilities, they would be like, or compute something. There could be multiple choice. There could be fill in the blank. On the quiz, there were things that were true. Were there true, false? No, on the homework, there were some true, false. So yes, there could be true, false, multiple choice, fill in the blank, short answer, simple calculations. All of that could be some variety of that. And on Wednesday, I'm going to give a very quick review, and I'll probably have a handout for that for all the material that we have covered so far. And I'm going to be using the Blackboard to do it, so we will not be having a recorded session of Wednesday's lecture. Any other questions before we get started? No? All right. So today we're going to talk about two probability laws, which in fact we actually saw. You have seen them, but we haven't actually pointed them out explicitly. So you've seen them behind the scenes, and now we're going to explicitly name them. And we'll also we'll continue where we left off on Friday. Speaking of which, on Friday we did start looking at hypothesis tests for averages, and that will not be on the midterm on Friday. That last example that we did really quickly, that will not be on the midterm. Okay, so recall the 0-1 box. What we discovered on our last lecture. I forgot what? Oh, thanks. I forgot the square root. I have it down here, but I don't have it up there. There should be a square root on that, and I know Sophie's going to say, please change it. If I can quit this. So we found, I'm just going to, now I've lost my little, okay, I'm just going to type it in here like it's an R function, the square root of p times 1 minus p. So we found that the box average, when we have a 0-1 box, is the proportion of ones in that box, which we name p. And the box SD was the square root of p times 1 minus p, which we figured out by using R to look at what that SD of the box looked like for various values of p, and then we figured out what curve exactly went through all the points. Now, when I have n draws with replacement, then I would expect about n times p ones, or so my count from the box is n times p, and the standard deviation for that, that shouldn't say expected, the standard deviation for the account, so the expected spread should be square root of n times p times 1 minus p. So here's an example where we can actually sort of see how this experiment might unfold if we were to draw 1,000 times from the box, keeping track of every single draw. So not just summing it up at the end, but actually watching every single draw. That's looking at one draw is like a binomial with n being 1. So we could just take one draw from that box, or instead of the R binom, I could have put in a sample from a box of zeros and ones where I sample one draw. So in this case, the chance of getting a 1 is 0.3. And I do this 1,000 times. Then I can look at, for example, the first 12 draws. And I see that the first draw was a 1, the second's a 0, the third's a 0, the fourth is a 0, the fifth's a 1, the sixth is a 0, etc. It's got ones and zeros coming out of that box. If I do a cumulative sum, I can sort of keep track of what the sum would be after each number of draws. So after 1 draw, my sum is 1. After 2 draws, my sum is 1. After 3 and 4 draws, my sum is 1. And after 5 draws, my sum is 2. After 6 draws, my sum is 2, etc. And then I could look at, well, how does the proportion change as I continue making my draws? And so I would divide by the number of draws from the box. And I can look at the first 10 of them and see that if I looked at the proportion of ones after 1 draw from the box, it's 1, because I drew a draw from the box. I drew a 1 from the box. After 2 draws, I have a 1 and a 0, so the proportion of ones is a half. After 3 draws, I've now drawn a 1 and 2 zeros, so the proportion of ones drops to a third. And after 4 draws, it's dropped to a quarter. Then after 5 draws, I now have 2 ones and 3 zeros, so I'm back up to 40%. So you see that there's a lot of fluctuation going on in how the proportion of ones drawn from the box changes, and that's reflecting the random process going on. We don't expect to always get 0.3 as the proportion of ones drawn from the box. In fact, it's really hard to get 0.3 until we have many, many draws from the box. So here's a plot of what's going on for the 1,000 draws. So let's take a look at the plot on the left. The plot on the left, the title says sum of draws. So what that is keeping track of how many ones I've seen. If I had, this is just one instance of draw after draw after draw 1,000 times. After 200 draws, how many ones do I have? Looks like maybe 50. How many ones do you expect to see after 1,000 draws? How many ones do you expect to have seen in 1,000 draws? What's that? 300. And what does it look like? It looks like I'm higher than that, right? Right. But I'm up around there. Now, if I instead look at the proportion of ones that I've drawn, remember when we first started, this is for a different set of 1,000, which is coming down from 0. If your first draw is a 0, then the proportion of ones is 0. And look at the fluctuations. The fluctuations are quite big at the beginning, and then they settle down. You see that it's settling down to 0.3, which is what we'd expect. We'd expect to get about 30%. And the fluctuations are large, and they eventually go down. They get smaller and smaller as we increase the number of draws. What I've plotted in these gray lines is the middle gray line is 0.3, so that you can see that the proportion of ones that I'm drawing has quite a large fluctuation and is settling down. The upper and the lower gray lines are looking at a band where by the time I get to 1,000, I would expect that the proportion of ones would be within this, these upper and lower bands. And that is plus or minus 2 standard deviations of the observed proportion. Okay? So here's a mystery box. It's not a 0-1 box. It's got tickets in it with numbers on them, and I'm not telling you what the numbers are. And I want you to look at this. Is it a 0-1 box? First question. And how can you tell if it's a 0 or 0-1 box or not? Yes?
It's not a 0-1 box. You have to have 1,000 draws. You have over 2,000. And there's just one max to get 1,000.
After 1,000 draws, you notice that the sum of the draws, after 1,000 draws, my sum is 2,000. If it were 0-1 box, what would the biggest it could be? 1,000. So it's definitely not a 0-1 box. As if I put all ones in that 0-1 box, it would be exactly 1,000 by the time I get, and that's as big as it could get. All right, so it's not a 0-1 box, and we know why it's not. So what can you estimate about the box, given these 2 pieces of information I've given you? Yes? You want to say? You said it's a box of twos. Not quite, but that's a very good observation. You see that the average of the draws is settling in on 2. So I wouldn't necessarily say that everything in the box was 2, because if everything in the box were 2, what would happen with the sum of the draws? Yes, that's what you're saying. It's a straight line? Is that what you're saying? Yes. There would be no deviations whatsoever. I'd always be drawing 2 from the box. So the sum of the draws would always be twice the number of draws, and the average of the draws would always be 2. And that's not happening here. I've got things fluctuating up and down. But where does 2 come in? Yes?
You could have a box of 0 and 4 where the probability is that they're 50% zeros, 50% 4.
So you could have a box that had half zeros and half 4s, so the average of the box was 2. That's right. That's not this box, but that's what you can deduce from this, is that the average of the box looks like it's about 2. Here's the actual box. It's one that you close to one that you worked with. I made a typo. It's 1124. It's one that you've worked with already, where you have computed the box average, and you actually computed the box SD. And I'm just going to fix this. I think I need someone to preview my slides before I show them to you. And the box average is 2, and the box SD is 1.22. Now we can continue with that and say our expected sum when we're drawing should be n times the box average. So that would be n times 2, or 2n. And the SD of the sum, similar to what we saw with the 0, 1 box, should be like the square root of n times the box SD. Then the expected average should be the box average. And the standard deviation for the average, we saw that that's fluctuating but getting closer and closer to 2. It's like the box SD divided by the square root of n. Sharetta? Yes. Yes. N's the number of draws. That's what we looked at was from 1 to 1,000. That's right. Any other questions? So what I'm bringing it back, and I'm now plotting. I'm actually now plotting the expected sum and the expected average. And on the left plot, I zoomed in to only look at 800 to 1,000. And the light gray line is 2 times n. So it's the expected sum, which is 2 times the number of draws. And on the right-hand plot, I have put a horizontal line at 2. And then I've gone up 2 standard deviations and down 2 standard deviations, which is the SD of the box, 1.22, divided by the square root of n. And those lines are for 1,000 draws. Okay. So what do you notice about the left plot? Dan? And a lot bigger. So the actual sum that I'm observing is above and quite a bit above the expected sum. Is that really unusual? Why not? You're right. It's not. It's not really unusual. That gets to, well, where should it be, or where could it be, and be considered reasonable? Remember what the standard deviation of the sum was? It's the square root of the number of draws times the SD of the box, right? So that's, what's the square root of 1,000? All right. What's the square root of 900? 30. All right. And 30 times 1.22? Maybe I'll make sure no calculators are allowed on the test. 36. Okay. So does it look like I might be within 36? Or that's only one standard deviation. Two standard deviations would be about 72, 75. Does it look like I'm within around 900? After 900 draws, does it look like I'm within plus or minus 75 of the expected 1800? Yes. So in fact, I am far away, but I'm not so far away in terms of this, the standard deviation for the sum. So that's one of the rules of probability we're learning about today, is when I'm looking at sums of draws, I know that my expected sum should be n times the box average, but the actual observed sum can vary quite a bit from the expectation. And how it varies is based on the standard deviation for that sum, and that's root n times the box SD. And so that gets bigger and bigger as I draw more and more. So my sum can get quite far away. My observed sum can get quite far away from what I expect. On the other hand, what's going on with the average of the draws from the box? It starts really fluctuating a lot, but it gets closer and closer to the box average of 2. And if I think about, well, what's the standard deviation for the average? That's the box SD divided by the square root of n. So if I again take 900 as my example, because I can take the square root of 900, that's 30. And my box SD is 1.2. So I now have 1.2 over 30. Can anybody tell me roughly what that is? So let's look at two of them. Two SDs would be 2 times 1.2 over 30, which is 2.5 over 30. So it's like a ninth or so, right? Eighth? Ninth? And am I roughly within? So there's 2.5. So you can sort of see where two SDs are for 1,000. But for 900, I'm definitely within 2 standard deviations of what I expect. So what's going on when I'm looking at the average of the draws from the box, as I draw more and more, that should get closer and closer to the box average. And the spread that I expect to see is shrinking, like 1 over the square root of n. So this is it. This is the probability law. If you have a large number of draws from a box, if we have n is the number of draws from a box, the expected sum is n times the box average. But the deviation that we might see, and that's represented by the standard deviation of the sum, the deviation that we see grows as the sample grows, as we draw more and more from the box. So the deviation grows, and typical deviations are the square root of n times the SD of the box. On the other hand, if we take the average draw of the draws from the box, that gets closer and closer to the box average. And the deviations get smaller and smaller because we're dividing by n, right? So the typical deviation is the SD of the box divided by the square root of n. Okay? So that's called the law of large numbers. All right. So we have the power of using R is we have uncovered this law of large numbers through observation, essentially. And if I just go back to this, you see the observed sum deviating from the expected sum, whereas the observed average is getting closer and closer to the expected average. Okay. All right. Now we're going to switch over to looking at hypothesis tests where we don't have a 0, 1 box in the background. We have numbers in our box, but they're not zeros and ones. So as I will bring back the note that I put at the very first page. You might not have noticed on the title slide, which says these examples are all made up. Okay. Although they are actually, each one of them is based in data that was actually collected, or based in some sort of real example. This actually, there is a concern about the safety of this water, and samples of the water were taken, and it was the coliform levels in this water were measured. But the measurements I've made up, and the safety levels I have made up. And I've just made them up to make it easy for us to look at, to do this hypothesis test. So the question is the water safe? And there are safe levels, which I have determined. I actually went to the EPA website last night, and they have all these, it's like when you drive a car and there are these idiot lights on your dashboard. They don't actually tell you the oil pressure and those sorts of things. They just turns a light on when it says, hey, dummy, get off the road, your oil pressure's too low. Well, it's like that here, where you send your water sample off to a lab and it comes back saying, oh, this is really bad. You've got to do something about it. So I've tried very hard, but I could not find the actual. There are levels at which the amount of coliform is too high, which would trigger a need for some kind of remediation. I couldn't find those levels, so that's the 250 that I have made up. So again, it's like these sort of idiot tests that come back from the laboratory. But suppose instead we actually knew that the level at which it was too high. The EPA does determine these kinds of levels, after which the water would be determined as to be unsafe, and you shouldn't drink or bathe in it. So you take 6 samples and you send it off to a lab for testing, and the laboratory says, our results are very accurate. We can determine the levels of coliform to a level of 50, and so you're going to get your numbers back, and you want to know, is my water unsafe or not? So let me stop before I go to the next page, and can you tell me can you see a hypothesis test kind of lurking there in the background? How might you formulate this? What might a null hypothesis be? And an alternative hypothesis. What could those be? What might a box model be? Yes? No, your first idea was a good one. Right. You care about this 250 mark. You don't want to be above it. You want to be below it. And so, typically, which one of those do we choose for our null? Would we choose for our null hypothesis? Remember, that's the devil's advocate, the skeptic. Which of those two would you choose as your null hypothesis? The other way around. You would want to be a skeptic. The skeptic says, your water's just fine. Don't worry about it. Or maybe I should say you want to be. So that's. I see why you would say, the skeptic would say above 250. So let's say this. You're coming from the point of view of saying there's nothing strange going on. How about that? That makes a little more sense. There's nothing strange going on. So that says your null hypothesis would be your levels, the level of coliform in your water is less than or equal to 250, or less than 250, either way. And the alternative is that, there's something going on, and it's bigger than 250. But it's that your water level, so do you expect the results of the test if your water level is below, or the contamination in your water is below 250? Are the 6 results coming back all going to be identical? No, why not? Saw you shake your head, no? Due to random variation in the laboratory processing and even possible to the water, you don't expect them all to be identical. In fact, the lab has said we're accurate to about 50. And so, so the null hypothesis says also that the fluctuations are just due to the chance error going on in the, let's say, the laboratory setting. And so we have a box of lab errors. The lab has advertised that they have extremely accurate and precise instruments. We would say the expected error is 0, and the standard deviation of the error is about 50. And so you saw this measurement error model way back when we first introduced design of experiments. Okay, so here's our actual data. We observed the lab sent us back 6 results for our 6 samples, and the average is 285. And the expected average is 250. Yes, 250. So we're above that. And our null hypothesis says, hey, you know what? That's just the kind of fluctuation that you get from this error model. So I want to see how far above am I. So I take my observed average, 285. I take my expected average, 250. And I want to say, well, how far away are they? Well, I would like to look at that in terms of the kind of variability I would expect to see drawing from this box. So I would divide by the SD for the average. What is the SD for the average? Now that you know those probability laws for averages and SDs, what would you say? When you're taking draws with replacement from a box, what's the box SD? Remember? Should I back up? 50. The box SD is 50. How many draws do I have from the box? 6. So the SD of the average should be 50 divided by square root of 6. I didn't pick a very nice square rootable number, did I? But that's what it would be. So the null distribution says that there's nothing bad about your water, that what we've observed is just the chance fluctuation that we would see in the process of measuring the coliform levels for your water. And so let's begin by taking one more assumption, and that's the assumption we talked about with measurement processes, is that often the errors look like normal curves. So let's assume that the tickets in the box, if we were to make a histogram or a density plot, of the tickets in the box, it would look roughly normal. So we've said that that should be centered at 0, and the lab has told us that the spread is 50. And so we can then, we've just answered all these questions. What's the box average? 0. What's the box SD? 50. Let me ask you this. What's the probability distribution for one draw from the box? So if I were to draw once from the box and put it back, and then replicate that 1,000,000 times, and look at all the draws I've had from the box, what would that look like? That should look roughly, we can experiment. We can actually try it. Does anybody want to guess? No? Okay. What about the probability distribution for the average of 6 draws from the box? Tell me, what do you expect the average of 6 draws from the box to be? If there's nothing going on. 250 is what we're going to assume. And the SD would be 50 divided by the square root of 6. So we can now go to R and check it out. Let's try that. Here we are in R. So how do I do it? I have a box of normal errors, and I want to look to see if I take one draw from the box, I'd like to know what its probability distribution is. One draw. How do I figure that out? Yeah, what are we trying to find? So when you had a box that had a 1, a 1, a 2, and a 4 in it, and you took one draw from that box, and you had to come up with a probability distribution for that, what's the chance you observed a 1? A half. What's the chance you observed a 2? A quarter. Chance you observed a 4? A quarter. So you knew the probability distribution for one draw from that box. Okay, now you've got normal curve generating the draws from the box. Centered at centered at 250 and spread of 50. And I'm asking you, what would the probability distribution of one draw from that box look like? So how do I even get a draw from that box? Oops, this is the problem with sometimes making, okay, so I'm backing up. We're not even going to go there yet. How would I generate one draw from that box? Yeah?
Create the box with the numbers in it and then take a sample.
Good. So how do I create a box with tickets where the box looks like a normal? So this is when we get into that world of, it was really easy to create this box, right? Box is C1, 1, maybe 2, 4. And then I could say one draw, I would sample from that box one time. And then I could sample again, and I could sample again, and I could sample again. And I could then say, well, if I wanted to look at the distribution, I know what it is. But I could actually take, and I could replicate 100,000 times a sample. Well, I'm not going to do it that many. 1,000 times sample box 1, and those would be my draws. And I could table my draws. You all did this on your homework, and I saw, oh, look, 491 ones out of 1,000. So that's roughly a half, which is what I had said the probability distribution was. Now I got to somehow stick a normal thing in there and draw from it. So there's a slight funny thing going on here. How do I stick a normal in the box?
You could put a number of cards in the box that would lead to that sort of normal distribution.
We could, and it's really hard, though. Why is it really hard?
I don't know how to do it.
You don't know how to do it. I don't know how to do it either. Well, I could kind of get there, maybe. But part of the problem is that here's the, let's draw a picture of the normal. So let's look at a curve of the normal with a mean of 250 and an SD of 50. And I saw it pop up. Oh, hang on. Let me just quickly change this. Wait, that's kind of weird. I don't know why I must have specified something else that I don't know about. That's strange. Here, let me do a, there we go. Oh, it's big, but that looks, oh, let's do it. There we go. There's my normal coming. It's taking me a while to get my limits right, but there we have, centered at 250. And let me see if I could shrink it so we can see it. So the problem is we've got this smooth curve. And it sort of says, well, any value is possible. So I could say, well, I can only measure to the nearest unit. So I could figure out, well, what's the chance of getting 250, 251, 252? Remember, we're back to the density curve era. And that means that the area under the curve should be my probability. So I could work it out. On the other hand, R actually gives me a box already and samples from a normal for me. Or close, R norm. R norm says, hey, I'll give you a draw from a box that's got a normal curve in it. It's like, that's good for me. So if I say R norm 1, mean equals 250, SD equals 50. There it is. My first observation, my one draw from the box is 219.1 whatever. The next one's 257, 178, 235, 331. We can go like that. So, yes? Can you get what? You can fix it afterwards. You can round it if you want a whole number like that. Well, it's got a few different things. Round says there's the ceiling function, which rounds up. The floor function rounds down. And the round function, which does, so anything you want. Yeah. Okay. All right, so now I can do what I was doing with my simple box, 1, 1, 2, 4. I can say, hey, replicate. Here are my draws. I can say replicate this process 100,000 times of taking a draw from a normal with mean 250 and SD 50. And then I can say, well, give me a density plot of these draws. And there it is. I should have made you guess before I showed it to you. But it looks like the box. We actually should have known that already, right? Because we know that when we draw one ticket from a box, that the probability distribution looks like the table of tickets in the box. So same thing, when we've got our normal curve in the box, I draw once, that the chance that I get whatever ticket value follows the normal curve. In fact, what I did doing that replicate, I didn't really have to do. I could just have used the R norm to say, give me 1,000 or 100,000. And it says, sure, okay, I'll give you 100,000 draws from this box. And there it is. Okay, so my next question, which unfortunately we're out of time, but let me just quickly show you the code. My next question said, well, what does it look like to have an average of 6 draws from that box? So I could take now 6 draws from that box, take the average of those 6 draws, and assign that to averages. And, oh, should have been mean. And then I can plot it. Plot density of averages. And tell me what you think it's going to look like. Will it look normal? Yes or no? Yes. Will it be centered at 250? Yes or no? Yes. Will it have an SD of 50? No. 50 over the square root of 6. It should look narrower. Does it look narrower? Thank you for saying that. You probably can't tell. All right, I'll see you all on Wednesday.